Yeah, see, I treat it like postcard. And you go like this.
It's more of a amorphous thing, but you got something about like this person's work.
We start at 2:40?
No, I think 2:45, no? Or we started 2:40? Oh, yeah,
That's
right.
what the schedule says.
Oh, yeah, you're absolutely right. Let me just double check. All right, everyone. So we'll start our next talk of the session. It's a great pleasure to have with us Hyun Kyu Kim from IAS in Seoul. And he will tell us about central extensions of Thompson's group T and quantum Teichmüller theory.
Thank you for the introduction, and I'd like to thank Sam and Yash to organize this thing with me. This stuff is what I did when I was a graduate student, and after that a little bit. And then my research direction kind of bifurcated from this thing. But still, I hope you'll find some things out of my talk a little bit interesting. Especially the quantum Teichmüller theory is probably not everybody will be familiar with. So I'm going to give you a short introduction and then how it's related to the Thompson group T. So let me begin with very brief review of quantum Teichmüller theory. So it was kind of born in the 1990s. So the initial development was in 90s, and then it has been developed after. So let me first begin with the finite type story. So I'll let sigma be the finite type punctured surface. So it looks something like this with some genus and some number of punctures. So n punctures. And the condition is that there has to be at least one puncture, so I don't know what to do for closed surface. If anyone can figure out what to do for closed surface, that's going to be pretty good. And I also assume the Euler characteristic is negative. That's not that much to assume. Anyways, that's the basic setting. Is there a question? Maybe. Okay. And so we have to quantize the Teichmüller space. So let's Teich sigma to be the Teichmüller space. In fact, let me not really define what this is, because I'm not going to tell you all the details about the quantum Teichmüller theory, but only some results from it. So just roughly speaking, you can view it as a space of complete hyperbolic metrics. But I have to say what I require at the behavior near punctures, but let me not really go into that. So it's a smooth manifold with Fay-Peterson-Poisson structure, and the symmetry group is mapping class group. So let me write it as mod sigma. So it's the usual mapping class group. Orientation preserving self-diffuse morphisms up to isotopy. So it acts naturally on the Teichmüller space, preserving the Poisson structure that I'm interested in. So, so I didn't even say there's a Weil-Peterson Poisson structure. Therefore, it makes sense to quantize this manifold with, together with this group action in a certain consistent way. But as I said, I'm not going to go into so much detail. So it's kind of the basic setting. So we will consider a quantization. And I'm not even going to define this word very precisely, but as I said, I'm going to review only very small bit of all this story, so that the only certain things that I will be using for the Thompsongroup T. And then when I quantize this Teichmüller space with this Poisson structure, I have to take this mapping class group action into account, and you will see how it appears. So what I could do in principle is to formulate what I mean by quantization as a problem, and then give you a solution, a known solution. But I'm not even formulating a problem, I'm just giving a solution. I'm not trying to claim that this is the only solution, but this is probably the most well-known solution. And in this most well-known solution that works for punctured surface, we need to choose an extra data. So these are the input data of this quantization problem, whatever that means. But to solve it, what is used is the extra data called ideal triangulation. So choose ideal triangulation, let's say tau of the surface. So these things that I'm trying to briefly review about the finite type surface will have the analog later that will give us the Thompsongroup T. So ideal triangulation looks like you want to triangulate your punctured surface by simple path connecting the punctures. So you have to have quite a lot of edges to triangulate it. So this is a triangulation whose vertices, the set of vertices, is the set of all punctures. That's why it's called ideal. And all the edges are considered only up to homotopy or isotopy. And even up to isotopy, there are infinitely many choices of different ideal triangulations. You choose one. And the way how ideal triangulation is used is that once you choose an ideal triangulation, the result is such that we consider certain special set of functions on the Teichmüller space to be quantized. So roughly speaking, some coordinate system. So coordinate functions on Teichmüller space, maybe a little more. So the model that I'll be probably focusing more on is the shear coordinates of Thurston that's associated to ideal triangulation of the surface. And so you have a bunch of nice functions, and you want them to be like coordinate system, and then you want the Poisson brackets among these coordinate functions to be nice enough so that you can solve the quantization problem easily. And that's what it is. So very roughly speaking, quantization means that you want to replace the functions on the Teichmüller space by certain operators on a Hilbert space. So operators. on a Hilbert space. Usually infinite dimensional, so this, and you could do it for each chosen ideal triangulation. And you could be satisfied by just this much. I'm not even giving specific formulas, but you could do it. But the point is that there's no canonical choice of ideal triangulation, so you want your quantization result to be not dependent on the choice of ideal triangulation. So the whole point is, what happens if you choose a different ideal triangulation? Then you get a bunch of different functions depending on your new ideal triangulations. And your recipe of coming up with operators will give you operators on a different Hilbert space, a priori. And you want them to be compatible in certain sense. So you want to find a unitary operator that connects these two lines. So this is what you want to aim for. So unitary map, such that you want these operators and these operators to be sort of conjugated to each other. So it is, one way of saying it is that they should intertwine these two operator representations. So unitary intertwiner is what you want to look for every pair of ideal triangulations. So that's a very rough situation of what's going on. And one good way of packaging this story, this kind of assignment and this compatibility, is in terms of groupoid of ideal triangulations. So let me formulate that groupoid.
Is there supposed to be one intertwiner for every path between the two triangulations in some space of triangulations, or is it just supposed to be a unique one?
That's a good question. So I think the best situation is for every pair, this intertwiner should be unique up to constant. That's the best situation. Yes. But in practice, that's not how it is built. You'll see how it is actually built a little bit later. And I will call this groupoid Ptolemy groupoid. So I think there are at least two different ways of understanding the word groupoid. I am viewing it as a category where every morphism is invertible. So this is just a category. Pt of sigma. So it's a category. Just a convenient way of formulating this. So the set of objects is all ideal triangulations up to isotopy. And that's an infinite set. And to be more precise, I have to not just ideal triangulation, but also you have to remember the labeling of the edges, but that's a minor issue. And then I just defined this groupoid such that for every two objects, there's only one morphism, exactly one morphism. It's kind of a stupid looking groupoid. It's just one way of formalizing what I'm saying here. And then this assignment and this intertwiner can be said in terms of the category theory language a little bit. So that's what I'm going to do.
What's it called
Why is it called a Ptolemy groupoid? Yeah, for that, if I had given you all the formulas, then you might have agreed. So these, I think one way to say this is probably that word was used by Penner for the first time. And Penner was working with decorated Teichmüller space associated to ideal triangulations, and his functions, lambda length coordinates, when you change the ideal triangulation by exactly one edge, the coordinate change formula for the functions on the Teichmüller space looks like Ptolemy relation. But I'm not giving you the formula. Let me write down the formula then. Okay? I think if you ask too many questions in the earlier part of my talk, you will miss the more interesting part of. So this is the least interesting part. So this the classical Ptolemy relation, I guess, is Euclidean circle inscribed quadrilateral, and these are the length. I think it says something like, this is the usual Ptolemy relation. And there's a hyperbolic version of it. And that's what the Penner's lambda length coordinate satisfies when you have an ideal triangulation and you change exactly one edge. Then these coordinates satisfy that kind of relation. But let me not go into that. Anyways, I think that's why it's called Ptolemy. But maybe I'm wrong. Okay, so quantization can be viewed as a functor from this groupoid to the category of Hilbert spaces. That's why I am formulating in this way. So quantization is a I just said a functor, but to be more precise, projective functor. So this is the category, the groupoid version of the representation and projective representation, as you will see. So from the groupoid to what I'm writing as Hilb. So this is the category where objects are Hilbert spaces, and morphisms are unitary maps. And by projective, I mean the usual functor sends morphism, composition of morphism to composition of morphism, but projective means that composition goes up to composition up to multiplicative constant. And you will see that more explicitly soon, so let me not write that down. And also, one thing that I have to take into consideration is what you're seeing here, the mapping class group action. So let's remember that the mapping class group acts naturally on the groupoid of Ptolemy groupoid of ideal triangulations. And so I'm not being precise in much of what I'm saying right now. But anyways, since there is a group action by mapping class group on this Poisson manifold, you want your quantization to be either invariant or equivariant in the right sense, such that in effect, what you're actually quantizing is the quotient of the Teichmüller space by the mapping class group, which is the Riemann's classical moduli space. So that's what we're trying to do. So what we actually want to quantize is not really not just that projective functor, but you want that to have the right invariance or equivariance under the action of mapping class group. And one way of saying it is the following. So in fact, I can say that what we need, in fact, we need a projective functor that goes from the quotient groupoid to Hilbert space. So that's what I you you take, so this is still with not just one object, but some finitely many objects. And just pick any object, like represented by A ideal triangulation, and then ask what is the set of morphisms from it to itself. Before quotienting, there's only one morphism, but now if you quotient it, there are more morphisms. And you see that this automorphism group is exactly the mapping class group by construction. So out of this, one thing you can say, if you have such a projective functor from this quotient groupoid to Hilbert space category, is that, so what do you have? For every object here, you have a Hilbert space. For every morphism here, you have a unitary map, such that the composition goes to the composition of the constant. And if you fix one object, then the morphism from it to itself will go to some Hilbert space unitary map from it to itself. So that gives you a projective representation of this group. So I'm kind of extracting part of this data. So out of this, you get, let me call it rho, from mapping class groups. So before it was groupoid, but part of it is the group. Going to, let's say, U of H. So H is the Hilbert space that's associated to that chosen one object. By UH, I mean the unitary maps. Well, in the usual definition of representation of a group, here you will see GL, but I'm dealing with the unitary maps for Hilbert spaces. So that's what you get. So this is unitary and this is projective. So projective unitary representation of the mapping class group on some Hilbert space. So that's kind of what you would get if everything works. And by projective, let me now spell out more explicitly what I mean. So projective means that if you have two elements in the mapping class group, and compose, then usually you want this to be equal that, but it's now equal only of the constant. So this is some constant. Here a non-zero complex number, but everything is unitary map, so it's actually modulus 1 complex number. So for every pair of elements of mapping class group, you have a number. And you can easily prove that this is a group 2 cocycle. So that's what's going to appear later again. And wow. So to say a bit of how these are actually done in the practical sense, let me tell you a little bit how this quotient groupoid is really dealt with. So basically speaking, to deal with that quotient groupoid, they work with certain presentation. So you want to find some generating morphisms and the relations among the generating morphisms. And for this finite type surface, there is only one kind of generating morphism. Of course, there are a lot of them, but all of them look almost similar. So how to work with this groupoid? this quotient groupoid, meaning ideal triangulations considered up to mapping class group action, and changes of ideal triangulations. So as I said, let's think of working with a presentation, meaning generators and relations. So as a generator, the most well-known generator is the elementary move of this category called flip, which I actually drew here. So elementary move called flip at one edge. So that changes exactly one edge and doesn't change the other part. And it's a classical result that any two different triangulations are connected by finite sequence of flips. So if you know everything about flips, then
Is it considered that the puncture is only one?
when the puncture is only one,
I mean, you can count the number of edges at the puncture.
yes.
If you have 2 or 3 punctures, then you cannot do with the isomorphism of the triangulation by the action of the mapping class group binder.
So what is your concern? Let's say when there's only one puncture.
If there is only one puncture,
Yes.
I agree that there, in some sense, only one triangulation.
Yes.
But if there are many punctures, there can be. So you can count how many.
Oh, okay.
edges are added.
Well, maybe I don't mean to say that there's only one generator. I just say that the generators all look similar.
I see.
So this generator, I would like label it something like this. And so for all edges. And, well, to be more precise, you want to use the labeling set. But I'm not going into detail.
Okay.
Yes. And then, well, the other task is that what is a complete set of relations among flips, and that's also well known, like pentagon relations and so on. So then the task is that you want to find the right intertwining operator that you want to assign to flip, such that all the relations hold. So the task is that for each flip, you want to find the unitary operator, the intertwiner, satisfying everything you want it to satisfy. And that is done. And I'm not giving you the formula for that. This involves the special function called the quantum dilogarithm, and so on. And let me just give you the names of people who have came up with this for the first time. So done by Chekhov and Fock. And later this is developed by Fock and Goncharov to more general setting of quantum cluster varieties, and independently by Kashayev. So they're roughly speaking 2 developments independently, and both are in 90s. So that's the finite type story about quantum Teichmüller theory. So you might wonder where Thompson group can appear. And now we go into that. So we will be trying to apply this formalism to the universal case. And I can only be very brief, I guess. Universal case. So before going to universal, how did the finite type situation look like? You had some finite type surface with ideal triangulation. And if you draw this in the universal cover, the usual convention is that you want to stretch everything to geodesic so that the picture looks pretty. So if you live in the upper half plane, then it should look something like this. And if you draw the same thing in the open unit disk, which I will be using today, you will be something like that. And you would have to, for finite type, you would have to deal with either fundamental domain or the whole thing with some group action. But then the universal case means that you drop the invariance and then you actually deal with the infinite triangulation of the unit disk. So we let our surface to be sort of the open unit disk, but we still want to work with the triangulations. So with infinite ideal triangulation, let's say obtained as the inverse image. If you draw everything, then it's an infinite triangulation. And for unit disk, the infinite ideal triangulation, let me call it tessellation. Tessellation of D. So we want to do a similar thing as we did for finite type. And so we will be working with tessellations and different tessellations and changes of tessellations and operators associated to pairs of tessellations. And a convenient thing to do is to pick a standard reference tessellation, and I'll use the Ferry tessellation. The standard tessellation is called the Ferry tessellation. I'll call it tau Ferry on the open unit disk. And as I said, we usually draw everything using geodesic. So it goes on and on. And so the vertices all lie in the points at infinity. And the Ferry tessellation's vertices are all the rational points. So rational points in S1. Well, you might view it as RP1, as you saw before. So by rational, I mean rational here. And you can change it to there by Cayley transformation. And I'll be labeling these points by these rational numbers. For example, this is the infinity, this is 0, this is -1, this is 1, and this is -2, -1/2, and so on. And so the rule how to draw the Ferry tessellation is that for two rational points, there is an edge if and only if AD minus BC is 1. There's actually more algorithmic way to draw everything just starting from these 2 points. Like if you know one edge, then the next edge is you just add like you are a kid. So you'll have a lot of fun doing it. And so I fix a reference tessellation, and I have to talk about what happens if we choose a different tessellation. And here in this board that's coming down, we have seen that we know how to deal with one flip at a time. So the strategy is let's only deal with finitely many flips. So that's what I think is first considered by Penner. So Penner's model is that let's consider tessellations that differ by the standard one by finitely many flips. So Penner's model, let's say, from 93, is that we only consider tessellations tau that differ from the standard one, vary by finite sequence of flips, sequences of flips. So we're not actually dealing with all possible tessellations. And all this has to do with the universal Teichmüller space. And actually, in order to talk about universal Teichmüller space, I have to deal with more tessellations. But I'm going to refrain from saying anything about universal Teichmüller space and just try to get to Thompson group out of these flips of tessellations. So for example, the initial Ferry tessellation is, of course, included. It's allowed. And let's say if you flip here, then it becomes that, and everything else is the same. And then maybe I can flip here, then it becomes this, and everything else is the same. So in fact, you can figure out that such tessellations differ from Ferry only at a polygon. And outside that is same as Ferry. So these guys are equal to Ferry eventually. Meaning that outside a polygon, an ideal polygon, it's the same as Ferry, and I'm only going to deal with those tessellations. So these are the, and we'll be making a groupoid out of such tessellations. And what is the mapping class group analog? And so let me write it in a different board. So you want to come up with the right definition of mapping class group that fits into this story. So the usual mapping class group is the self-diffeomorphisms of the surface. So you do want to talk about the self-diffeomorphism of the open unit disk, but you want to preserve that kind of tessellations. So let me define such a mapping class group. Instead of saying mod, I'll put AR. That stands for asymptotically rigid. This is not how Penner formulated it. This is from later formulation by Funar, Sergiescu, mapping class group of the unit disk. And by that I mean, so orientation preserving. Whenever I say diffeo, I mean orientation preserving of the unit disk to itself that preserve Ferry tessellation eventually. As a set. It doesn't have to preserve it arc by arc, but as a set, it has to eventually preserve it, meaning outside a polygon. i.e. outside a polygon up to isotopy. So that's I tried to define such a mapping class group. So you apply this diffeomorphism to Fairy tessellation, then you will get a different tessellation, and I want that to be of this type, where it differs from Fairy outside, differs from Fairy only at a finite polygon. And then so now we have almost all the ingredients to apply to.
Do the isotopies also have to preserve the Fairy triangulation as a set outside of a polygon?
Isotopy fixing boundary all the time.
Oh. But not necessarily the Fairy triangulation as a set.
What do you mean? So here by isotopy, I mean it can't mess with the boundary circle.
Is it obvious why you needed only to preserve the Fairy as a set rather than edgewise?
You will see a version. You probably will see a version where I also require to preserve Fairy arcwise eventually, but here as a set. Maybe just wait a few more minutes and see if you're satisfied. So, well, anyways, I'm trying to apply this to the quantum Teichmüller theory formulation and see what I get. And before going to that, let's try to think about what this group is. So note that this action, everything is up to isotopy of the disk diffeomorphism up to isotopy fixing boundary all the time. So in fact, the action is completely described by the action on the circle. So you can just restrict to the action on the circle, and that's an injection. So you can ask, what is the image? So what are the things that eventually preserve Fairy as a set? So you can first think of what is the diffeomorphism that preserve Fairy as a set, not eventually, as a set on the nose. And you can easily see that those are the PSL to Z transformations. So those ones that preserve the Fairy as a set on the nose are exactly coming from the PSL to Z transformation of the open unit disk, are PSL to Z. And therefore, you can also see that these thing that preserves Fairy eventually is exactly the piecewise PSL to Z homeomorphisms. I think you can easily prove that the PSL2Z fractional linear automorphism of the open unit disk really does preserve the Fairy tessellation. And so I could call this a theorem that the image of this asymptotically rigid mapping class group in the homeomorphism of circle is the piecewise PSL2Z, which is usually called PPSL2Z. homeomorphisms of the circle. This is piecewise PSL2Z homeo.
Subgroup there and isomorphic.
Right. This is isomorphic, this is subgroup. With rational breakpoints.
Rationals together with infinity, right?
Yes, yes. That's right. And note is that, well, the whole title of the conference is piecewise linear, but this is not piecewise linear, but you had an idea from Yash's talk that piecewise PSL2Z can be translated into piecewise dyadic affine. And in his talk, there was, I think infinity was fixed, hence the Thompson group was F. In this case, infinity is not fixed, and the corresponding Thompson group is T. So this PPSL2Z, piecewise PSL2Z homeomorphism of the circle, is isomorphic to Thompson group T. So this is the piecewise affine or dyadic homeomorphisms, not of the interval, but interval where you identify 0 and 1. And as Yash put it, this isomorphism might be viewed as being remarkable. And so let's try to now really apply this to the quantum Teichmüller theory to get something. So we will again consider a groupoid, sort of the universal version of the Ptolemy groupoid. Universal Ptolemy groupoid. Let me call it PT. So the objects are not just tessellations. I need actually a marking to make the action of this group to be faithful. So tessellation with distinguished oriented edge. It's usually called marking. By this I mean, so you choose not just a tessellation that's same as very outside a finite polygon. You choose one edge with an orientation. That's a marking. And still, morphism for any two elements, any two objects is just one element. And then there is this action of the asymptotically rigid mapping class group acting on this groupoid. And so if you are able to apply quantum Teichmüller theory, yields projective functor this quotient groupoid to Hilbert space category. And out of that, you can also extract the projective unitary representation of this asymptotically rigid mapping class group. But this was isomorphic to all sorts of groups, PPSL to Z, also to the Thompsongroup T. So you do get a projective unitary representation of the Thompsongroup T. And what do we do with it? I have to use my time wisely. At least let me try to work with a presentation as before. So presentation. So this a quotient groupoid, let's say G to be the morphism set or the automorphism of that one object. And in fact, this quotient has only one object. So that's kind of different from finite type surface case. Anyways, this is the morphism set from that single object to itself. And the generators, so the finite type generators were the flips at edges. And here it's really, you only need one kind of flip, but with marking. So you just flip at that marked edge and don't change other part. And that's called alpha. And beta is you don't change ideal triangulation, but just change the marking. And these two generators generate the whole automorphism group. And so we have all this isomorphism between different groups. So I'm calling this G. Was by construction, it's same as this group that we are quotienting by, which is piecewise PSL to Z, which is Thompson group. And this we do have a presentation. You saw the presentation of F before, and T has a similar presentation. And using this presentation, you can actually turn this into presentation here. And that's what Lochak and Schneps did. And let me write part of it. So these relations, you do alpha 4 times gets to the identity, beta 3 times identity, alpha beta 5 times is 1. This is called the pentagon relation. And 2 more unpleasant looking commutator relation, which actually has a nice geometric meaning, but let me not go into that. So we have such a thing. And then the quantum Teichmüller theory gives us the projective unitary representation of this group. So let's try to get something out of that. At least I have to get to what I said in the title of the talk. Very quickly. So we have projective representation rho from T to unitary operators. So we have 2 generators, you have 2 operators. And what you do is you try to evaluate these operators at the relations. So let's see what happens. So this must be some constant times identity. It is the genuine identity if this was a representation, but this is a projective representation, so you have some constant. And it turns out that if you actually compute these operators, this is actually just 1, this is 1, this is some non-trivial number, and the other two commutator relations just 1. So this is from the Chekhov-Fock quantization. And so one way to understand the projective representation of a group in general is you can lift it to an honest representation of the central extension of that group. And you can actually read the presentation of the central extension from that relation. So this yields central extension. Let me call it T hat CF. CF means Chekhov-Fock of T by Z. So it could have been by U1, but actually you only need Z. And we just got a presentation of it. So this is just alpha, beta with the central generator, where Z is commutes with the generators. And you just read what we have seen equals Z, and the others are 1. So you explicitly get a central extension presentation from quantum Teichmüller theory. And then what you can ask is, what is the central extension? So one thing is that what classifies all the central extensions of T by Z is the second group cohomology of T by Z coefficients. So this yields a class, a well-defined cohomology class in second group cohomology with Z coefficients. And G-Sen Sergiescu says that this is generated by two classes. One is called chi, one is called alpha. So two copies of Z, where this is the Euler class, and this is the discrete Godbillon class. And then I can ask, what is this central extension correspond to? I can tell you what that is, but I was going to tell you a lot more interesting way of realizing the same thing, not from representation, but from topology. But I don't know if I'll have time. Let me be very quick. So the result of Funar and Sergiescu 2010 is that this is a multiple of the Euler class. And what I did is you do the same thing, but using the Kashayev quantum Teichmüller theory, you actually get a different thing, but not Godbillon. But before finishing, let me at least very briefly sketch a topological construction of the same central extension. So we had D, open unit disk with infinite tessellation. Consider D star, which is the same D, but now you introduce puncture at every edge. So it's an infinitely punctured disk, but you still remember this structure, these arcs. And so define T star to be the asymptotically rigid diffeo of this thing that preserves this picture eventually as a set. Then by forgetting all the punctures, this projects to T. and the kernel is infinite Ray group. So you actually get this is an extension of Thompson group by infinite Ray group. This is called a braided Ptolemy-Thompson group. And what Funar and Sergiescu did is that you want to abelianize the B infinity. So meaning quotient by commutator of B infinity everywhere. Then abelianization of B infinity is actually Z. It's kind of easy to see. And you get some extension this way. And you can prove that this is central. So this is another central extension of T. And the theorem of Funar and Sergiescu is that this is isomorphic to the Chekhov-Fock central extension that we have seen. And there's a similar way of realizing this guy. And the question, which I will end my talk to, is how to realize the Godbillon Veil class. And I'll finish. Thank you.
Can you repeat what D star is?
D star is? So you take the Fourier tessellation, choose a specific point like midpoint in some sense, and just puncture. So it's D minus some infinitely many points.
Oh.
Some infinite type surface. And then you ask, what is the homeomorphism or diffeo that preserve this picture that I just drew, so these infinite many arcs, eventually as a set. So it can mess only at the finite part.
Should I have been able to see that I would only get multiples of the Euler class from these quantization constructions? Is that like something that you should be able to predict, or is it surprising?
I don't know. So the actual research direction that I wanted to go when I was a student is a completely different direction than what I'm saying here. But one thing that I was trying is to say, come up with some version of Teichmüller space kind of story that gives this class. I don't know whether I can prove that these kind of stories cannot really give this class. That might be true, might not be. What is possible is that there is a topological picture that realizes alpha, and that's actually what connects to Greenberg's work. So Greenberg and Sergiescu. So they have not this kind of surface, but some different infinite type surface. So some surface sigma with this kind of structure drawn on it, and then you ask some kind of asymptotically rigid mapping class group of this particular infinite type surface, and then the situation is similar that that mapping class group is an extension of T by infinite break group, so by relative abelianization, you get some central extension, and their construction gives alpha class. So one thing is you might want to use this surface and maybe try to apply the quantum Teichmüller theory to that surface. That's one thing that I have tried but never worked.
But the covering of this surface is, in fact, your Fourier selection.
You mean this surface?
Yes, if you take the covering, so the action should be something equivariant action.
I don't know if I understand your question. We can talk later. Yes. So, well, I didn't really write down the 2 more relations. It's like 5 relations, and 2 relations is some horrible looking commutators. But geometrically what it means is that you kind of see what the geometric meaning of these 3 relations, like alpha 4 times means like without the orientation, flip twice is the same picture. That's what the first relation is saying. Second relation is just you go around a triangle 3 times, like the same thing. This is the pentagon relation, the famous one. The 2 commutator relation says that the flip that's far away commute. So they also have a nice geometric meaning. And to realize alpha, one of the 2 commutation relations should be non-trivial. And it's kind of hard to expect to see from quantum Teichmüller theory, I think. But there is a topological model that does that.
Thank you again.
Thanks.
So we resume at 4. It's a very interesting talk. Really good. Wow, this is cool, and it's kind of a very natural question, like this.
I've written that up in the file.
Yeah, great.
Yeah,
Fantastic.
a little bit.
Why,
So this is,
why did you start with this sphere triangulation? Why not with a different one?
That's right. I think here,
If you take a different one, would you get a different?
you know, I think what matters, what really matters is just the combinatorial structure. So I don't think it's the Ferry tessellation that matters. It's just that, I don't know, I think nobody really, in this literature, nobody really asked that question. But if you really think about it, it's just a dyadic structure that you use.
Okay.
So it doesn't really have to be Ferry tessellation.
trying to remember things I learned a long time ago. So for the difficult diffeomorphism, they got beyond the classes giving like the Virasoro
Yes.
central extension, right?
That's why it's more interesting, I guess.
Yeah.
Yes, yes.
So do you know some way that the Virasoro algebra? Or
No. So
and
I think that's kind of what I had in mind. So this came out of the work that I was trying with my advisor when I was a student, and that's probably where we are trying to get at. Like if you you might want to view T as sort of discrete version of the circle diffeomorphism group, and hence realizing alpha is like working with the Virasoro group.
Yes.
So of course that's what you want to get at, but we never really.
I don't understand the meaning of a Virasoro, why people care so much.
Okay.
Quantum physics, what is the central charge and blah, blah,
That's
blah,
right,
blah.
that's right.
I think if you get some intuition of certainly the names, Bender, Fock, and people know about this, the meaning, right? So,
but I don't know. So, well, the way how I present it here is that this T came from this kind of mapping class group of this universal sort of surface, which is the open unit disk. That's why you can see immediately how T embeds into homeo of the circle, but maybe that's a disguise. Then it makes me think that it should be maybe it's better be a subgroup of
what I see
diff
is
S1.
you have PSL2Z, saying the Ferry tessellation is invariant under PSL2Z, and,
Yes.
and basically what thing you are doing is that you are lifting PSL2 of Z. Not really, because this is a free product.
And you know, one other thing that used to bother me is that this T, which is the I was trying to make the point that this is kind of the universal version of the mapping class group, but the genuine universal version of the mapping class group should be something that contains all the finite type mapping class groups. This one does not, because the finite type mapping class group is contained only in the completion, because the finite type ones, they don't involve just a single flip. They involve periodic flips.
Sure.
So this is maybe not the right model. This was convenient for certain things, as I presented today, but maybe that's not like the right group to work with in certain aspects.
Okay. Okay. That's interesting.
And also, for me also, it's been a while since I've thought about this. So what was your point? What was your question?
No, just, so Greenberg,
Yes, yes,
Sergiescu,
yes.
some surface has some genus.
Oh, so,
Sigma.
well, that infinite type surface is of genus 0.
Genus 0.
Yes.
So a lot of punctures.
Yes, infinitely many punctures.
Uh-huh.
It's basically, so we have seen the tree description of the Thompson group, and you first have to consider the infinite rooted binary tree, and the Thompson group can be thought of as almost automorphism of the infinite rooted binary tree, not the actual automorphism. So it sends leaves to leaves.
Yeah.
So that's kind of the basic motivation, I guess, of their surface. So you take the infinite rooted binary tree, you kind of thicken. So it's a surface that looks like the rooted binary tree. But then you have to attach, for every vertex, you have to attach a thin line that has infinite many punctures. And by using that, you can actually realize the Thompson group action into an actual mapping class of this infinite type surface. You have to move some punctures around. So it's not just this single surface and mapping class group. You have to say how T embeds into the mapping class group of this surface. And for that, they had to come up with the right way of moving around these punctures. So they only used a specific way to realize this Godbillon Veil class. But I think Funar and Sergiescu, they worked more generally so that maybe this way you realize some other classes too. But that question has never really been studied so much.
Other classes, you mean the combination of these?
Yeah, I don't know. Like, so what kind of classes can be realized?
Oh, really?
Yes.
Okay.
I think one general question was, what are the classes that can be geometrically realized? That was never really studied. Yes.
Okay. Thank you very much. Very good.
Thank you. You give a board talk?
Yeah.
Okay. Let me erase it for you.
Okay, no, I'll help.
Be aware, the moving is very slow.
Yeah. I noticed. I was like, he's doing such a good job of like filling the, everyone just kind of is casually talking while they're moving the board. I was like, okay.
Yeah, that's a skill that you learn after teaching a few years in the university. I think like erasing time is also the time.
Yeah, I'm good with erasing time, but I've taught with boards that slide horizontally, and I can just kind of like push it really fast, which I enjoy doing. I did slice my finger open one time on the board.
Oh no.
And I happened to have Band-Aids in my backpack, so I just like, the Band-Aid only kept going, but I think I kind of scared my students. They're like, why is she injuring herself?
So you bled?
Yes, and I kept writing, and then I see a few horrified looks, and I'm like, oh, I am bleeding. I think they were just like, who hurts themselves doing math? I was like, apparently me.
Maybe you want to practice a little bit.
No, I practiced during the break.
Okay.
In general, it's like you want the one that you just finished to go all the way to the top, right?
Yeah.
Yeah.
I don't know what's the best board to start with. You can think
I don't
about
really
it.
care.
You have to wear this somehow.
The world is not built for people without pockets. Okay, I'm a pretty loud speaker anyway. Oh, let's see, I write right-handed.